Hello, welcome to Fundamentals of Acoustics. This is the 7th week of this course, which is 12-week long. So, starting today we are going to enter into the second half of this course, and till so far what we have covered is a somewhat detailed treatment of 1D waves which travel in Cartesian frame of reference, that is planar waves. We have also introduced the concept of impedance, and we have developed some basic relations for spherical waves which are traveling outwards, that is when these waves do not get reflected and come back to the source. So, with that what we plan to do over this week is extend our discussion for 1D waves moving outwards in a spherical fashion, and specifically what we plan to do is to figure out what happens when two or more sources of such waves produce sound, and these sound patterns or sound waves interfere with each other and they are perceived, and what is the nature of these waves at a distance r away from these two or more sound sources. So, in other words, we are going to discuss how waves interfere with each other, and that is going to be pretty much the theme of the discussion for this week. So, as I mentioned, the theme of the discussion is going to be interference. So, we are going to discuss the interference of sound emanating from two specific sources, S1 and S2. So, these two sources are indicated here. This dotted line is the median line between these two sources, and the distance of source S1 from the median line is d over 2, and the distance of the second source from the median line is also d over 2. Both these sources are emitting sound, and what we are interested in is what happens. So, as sound is emitted, it gets propagated, and what we are interested in is what happens to the sound which is perceived at point P, and this point P is at a distance r at an angle theta away from these sources. So, what is r? We will draw that. So, r is the vector as indicated here. The distance between S1 and point P is R1, and the distance between S2 and point P is R2. The other thing is that we want to define what is theta. So, theta is the angle of between vector r and the median line. So, with this understanding, our aim is, so our goal is what is the value of pressure at point P, which is r distance away, theta angle away, and at any time. So, what is PRT? What is known? So, what we do know is that the volume velocity of sound source S1 is same as the volume velocity of sound source S2, and let us say we call it VV. So, Okay, so the volume velocity is not shown same, but the magnitude of volume velocity of source 1 and source 2 are same. So, this is the first thing which is known. The second thing which is known is that the difference in phase of VV1 minus VV2 so that phase is phi. Actually, it is the other way around. So, VV2 minus VV1 is phi. So, if these two parameters are known, that the volume velocity is Vv and the phase difference is phi, then we can say Vv1 volume velocity is equal to, so Vv1 is the magnitude of the volume velocity is Vv1, magnitude Vv times E minus J phi over 2, and Vv2 equals Vv its magnitude times E j phi over 2. So, again, so with this knowledge we are interested in finding P r t, P r theta t, which is the pressure at location r at an angle theta for a time t. So, we will write down this expression. So, pressure at point P, and this is capital P because it is complex pressure. So, complex pressure at point P is going to be complex pressure due to S1 plus complex pressure due to S2. So, we will write down each of these expressions. So, what is the complex pressure due to S1? So, it is Vv over 4 pi r1 j omega rho naught E minus j omega r1 c E j omega t. So, where did we get this expression from? In last class we had developed the expression between volume velocity and complex pressure. So, this is the complex pressure due to S1, and similarly the complex pressure due to S2 is Vv divided by 4 pi R2, because the second source is R2 distance away from point P, times j omega rho naught E minus j omega R2c E j omega t. Okay. So, let us call this equation 1. Now, what we have done here is that in equation 1 we have expressed complex pressure at point P in terms of R1 and R2. So, now what we will do is we will develop an expression between R1, R2, D and theta. So, if R is extremely large compared to D, which means that this point is extremely far away, then let us look at that. So, if I drop a normal, this angle will be 90 degrees, this will be theta. Okay. So, if I am very far away, the point P is extremely far away, then R, vector R and R1, they will be almost parallel to each other, they will be almost parallel to each other. In such a case, so if R is extremely large compared to D, then in such a case R1 is equal to, so this distance, so R1 is equal to R minus D over 2 sin theta, and R2 is equal to R plus D over 2 sin theta. So, with this understanding, so what we do is we put R1 from here and we put R2 from this relation. So, using this what we get is P R theta t equals, now what I will do is I will take some of the components, some of the portions of this equation as common sum terms. So, V V j omega rho naught e to the power of j omega t is common, and also common is divided by 4 pi. So, in the brackets I get e to the power of minus j omega r minus d over 2 sin theta divided by r minus d over 2 sin theta plus e to the power of j omega, there has to be a negative sign, times r plus d over 2 sin theta, and there is also a c here, divided by r plus d over 2 sin theta. Okay. Now, if r is extremely large compared to d, then in this term d over 2 sin theta, maximum value of sin theta is 1. So, the product of d over 2 and sin theta can never exceed d over 2, and if r is extremely small, large compared to d, then in this thing this can be approximated as r. Similarly, this term in the denominator can be approximated as r. Okay. So, I am going to rewrite my expression P r theta t is equal to V V j omega rho naught E j omega t divided by r. Now, the other thing is that one may do a similar approximation in this term also, but then that will not be mathematically wise. Why do I say that? So, just consider this, e to the power of minus j omega r minus d by 2 sin theta c is equal to what? It is cosine of omega r minus d over 2 sin theta times c plus, so actually there is a minus sign, so it has to be minus j sin omega r plus d over 2 sin theta c. So, actually there is a small error in this, should be divided by c. Okay. Now, here I cannot drop the d over 2 sin theta term. Why can I not drop it? I cannot drop it for the simple reason that suppose d over 2 sin theta times omega by c. Suppose its value comes to be, let us say, pi over 3 radians, suppose, and omega r over c, it comes to be, let us say, r is extremely large. So, it may be, let us say, r is 20,000 radians. But then an addition of pi over 3 will cause a significant change in the cosine of this angle. If the cosine of, right, if this number is pi over 2, then so small changes in d over 2 sine theta times omega over c can cause significant changes in the cosine and sine of this angle. So, I cannot make the same approximation in this term which is encircled in the purple circle. Okay. I cannot do the same thing here. So, here I have to retain this, otherwise I will be making a mistake. So, with that understanding, what we have to do is we have to retain it and do the correct mathematics. So, I am going to erase this because I need some space. So, I will continue writing this expression. So, the other thing I can do is I can take e to the power of minus j omega r over c outside the bracket. So, I have taken it outside the bracket, and in the bracket I have e minus j omega d sin theta over 2 c, and minus become positive, plus e, and here minus and positive became negative. So, minus j omega d sin theta divided by 2 c. Okay. And then I think I made an important unforgivable mistake. So, when I was doing this substitution for volume velocities, I should have also included the phase term, which I did not. So, I will do that, I will rectify that mistake here. So, here it has to be E minus j phi over 2, and here it has to be E j phi over 2. Same thing here, E minus j phi over 2 and E j phi over 2. Okay. So, here it is minus j phi over 2 and this is E j phi over 2. So, volume velocity magnitude j omega rho naught E j omega t minus r over c divided by 4 pi r times exponent of j omega d sin theta over 2 minus phi over 2 plus E minus j omega d sin theta over 2 c minus phi over 2. Okay. So, let us call this expression as A1. So, this is A1 and this expression in the parenthesis is what? So, this is something like E exponent j to the power of beta plus exponent minus j to the power of beta. So, this is A1 times, so this is equal to A1 cosine omega d sin theta over 2 minus phi over 2. So, there should be a c here, yeah. So, that is there, and there will be a factor of 2 here. Now, omega d over 2c equals, so what is omega? Omega is 2 pi f d divided by 2 times f lambda. So, f that is the frequency, they get cancelled out. So, this is equal to, and 2 also gets cancelled out. So, this is equal to pi d over lambda. So, my expression for complex pressure at point P is equal to A1 times, or actually it is 2A1 times cosine pi d sin theta pi d sin theta divided by lambda minus phi over 2. So, that is my expression. So, what does this expression tell us? That if there are two sound sources, S1 and S2 separated by a total distance d, then the sound experienced by at point P, which is r distance away and at an angle theta, the complex pressure is expressed by this relation. Now, let us look at this expression in detail. What we observe is that A1, so what is A1? It is magnitude of volume velocity times j omega rho naught E j omega t minus r over c divided by 4 pi r. So, A1 does not depend it does not depend on what? It does not depend on theta, it does not depend on phase, and it does not depend on the distance between the two sources. It only depends on r and the angular frequency, right. It only depends on. So, if I have to, so and let us call this expression as this term as B. So, B, it depends on theta, d and phi. Okay. If I have to figure out that how is sound going to change in this picture. So, in this picture, as theta increases, this P is going to move like this. So, as theta changes, this P is going to move like this. So, for at a given distance r, as I increase or decrease theta, how will P change? That change will be decided by the behavior of B, because B is the parameter which depends on theta, phi and d. Okay. So, this is important to understand. So, if I have to plot the variation of pressure with respect to theta, then that plot will have same shape as the plot for B as I change theta. So, we will actually make one such plot. So, to construct a plot, we need to know the value of d, we need to know the value of theta, and we need to know the value of phi. So, we will make some assumptions. So, we assume that phi, which is the phase of the volume velocity source, is equal to pi over 2, and we pick d, that is the distance between the sources, such that d is equal to lambda over 4. So, then B equals cosine of pi times lambda over 4 times sin theta divided by lambda minus pi over 4. Okay. So, this is equal to cosine of pi over 4. So, lambda lambda cancels out times sin theta minus pi over 4. So, first let us construct a table. So, we will construct a table for B. So, let us say theta, so theta can have different values 0, pi over 2 radians, pi radians, 3 pi over 2 radians, and then of course 2 pi. Then what is the value of B? B is, so B is what? So, when theta equals 0, then it is cosine pi over 4 minus pi over 4, or when theta is equal to 0, then it is cosine pi over 4 minus pi over 4. So, that is minus, it is 1 over square root of 2. When theta equals pi over 2, then sin theta is 1, pi over 4 minus pi over 4 is 0. So, cosine of 0 is 1. When theta equals pi radians, then this is again 0 and the value of B comes to be 1 over square root of 2. When theta equals 270 degrees or 3 pi over 2 radians, then this is sin theta is minus 1. So, minus pi over 4 minus pi over 4 becomes minus pi over 2. So, this value becomes 0 and at 2 pi it is 1 over square root of 2. So, with these points we will draw a polar plot. So, in the polar plot this is 0 degrees, this is pi over 2 radians, this is pi radians and this is 3 pi over 2 radians. And what we will do is, so the distance, so this is my origin, so the distance from the origin will reflect the value of B. So, at x theta equals 0 degrees, it is what is it? It is 1 over root 2. It is 1 over root 2. Same thing here. At pi also it is 1 over root 2. So, the distance from the origin is same. At pi over 2 it is 1 and at 3 pi over 2 it is 0. So, my polar plot excuse me. So, it is a little so it will look something like this. Now, this dip on the negative side is not that sharp, it will be a little softer dip, but the point is, so this is the plot for B and what this says is that if point B is located at theta equals 90 degrees, which is here, then it will hear the maximum sound pressure level, because the value is 1 here. So, this is 1, this is 1 over root 2, this is 1 over root 2, and if our microphone is located at the other angle, which is minus 270 or which is 270 degrees, then the sound perceived by the microphone will be minimum and theoretically it will be 0 pascals. So, this is the effect of interference, and what we see is that when two sources interfere, even though two individually each source may be emitting a spherically symmetric wave, but if they are off in some phase difference, then they interfere with each other to produce some interesting polar patterns, and these polar patterns can be calculated using the methodology which we have discussed in this lecture. So, with this I conclude the discussion for today, and tomorrow we will continue our discussion on interference, but with different situation. So, thank you and have a great day. Bye.